Good morning. Today we will start our new topic in this course, which is simultaneous equation model. In many relationships, as we know, we have what's called a single equation type. This example, for example, this simple linear regression model, we have just one equation. We have single equation. And in this single equation, we have dependent variable, which is y, and y is represented using a linear function in the explanatory variable x. So in a single equation regression, we have just one dependent variable, one y, and this y is represented as function in some explanatory variables, which are the x's. But actually, there are some situations where we have a kind of two-way flow of influence. And what do we mean by two-way flow of influence? It means that one variable is affected by the other variable, and the other variable is in turn affected by the first variable. So sometimes the dependent variable is affected by the explanatory variables, and the explanatory variables are in turn affected by the dependent variable. So in this case, we have a kind of two-way flow of influence. In the first equation, or in the single equation, we have just one-way flow of influence where x influence y. But in a two-way flow of influence, we have x that may affect y and y may affect x. Thus, we need to consider two equations instead of one. We need one relating x to y and another one relating y to x. And actually, this is called simultaneous equation models, where we have more than one regression equation instead of one. We have more than one dependent variable represented in a set of explanatory variables. Now let us consider this example where we have y1 represented as function in y2 and x1. So in the first equation, we have a dependent variable, which is y1, and we have two explanatory variables, which are y2 and x1. y1 is affected by y2 and x1. But this y2 here, this explanatory variable y2 here, may be affected as well by y1 and x1 again. So in this case, we have to introduce another regression model, which is given by y2 as dependent variable and y1 as explanatory variable and x1 as explanatory variable. So in the first equation, we have y2 x1 explanatory, while in the second equation we have y1 x1 explanatory. Why? Because there is a kind of two-way flow of the influence between y1 and y2. There is a kind of switching places between y1 and y2. The y1 and y2 are switching their places. In the first equation, y1 is dependent and y2 is the explanatory. Then they switch the places. In the second equation, y2 became the dependent variable and y1 became the explanatory variable. They are switching the places. So y1 and y2 in this case are mutually dependent or are called endogenous variable. These y1 and y2 are called endogenous variable, and x1 is called exogenous variable. So the endogenous variable are the variables that are switching places between explanatory and dependent, while the exogenous variable are the variables that are completely explanatory. They are appearing only on the right hand side of the equations. So in simultaneous equation, we have two types of variables, the endogenous variable and the exogenous variable. And again, the endogenous variable are the variables that are switching their places from explanatory to dependent and from dependent to explanatory. They are the variables that may appear on the right hand side of the equation and on the left hand side of the equations, while the exogenous variable are the variables that are completely explanatory variables. These are x's that appear only on the right hand side of the equations. So now, if we have two equations like this one may think of, I can take each one separately and apply the OLS, the ordinary least square. But actually, remember the assumption of the OLS saying that the error term and the explanatory variables should be independent, meaning that in the first equation, u1 and y2 should be independent from each other. And in equation number 2, u2 and y1 should be independent from each other in order to be able to apply the OLS method. Again, remember the assumptions of OLS, which say that the explanatory variable and the error term are not correlated. So in order to apply the OLS, then u1 and y2 in the first equation should be independent, and u2 and y1 in the second equation again should be independent. If this assumption is satisfied, you can apply the OLS. While if this assumption is not satisfied, you cannot. Now let us check this assumption concerning simultaneous equation model. Now let me give you a common or a famous example in simultaneous equation, which is the supply and demand. Of course, we all know that the demand and supply can be represented by these three equations, where the quantity demanded is represented by the price, and the supply, again, the quantity supplied is represented by price again, and this is under an important condition of equilibrium. That's at the equilibrium point, the quantity demanded and the quantity supplied must be equal. So now we need to check whether u1 and pt in the first equation is independent or not, and in turn whether u2t and pt in the second equation are independent or not. So now let us assume that any changes have happened to u1. The factors affecting the quantity demanded have changed, all the factors except the price, of course. Any factor that could be income, wealth, tastes, even fashion, have affected the quantity demanded. So if the quantity demanded is affected due to error or due to any other factor except the price, so due to this equilibrium condition, if the quantity demanded changed, then the price and the quantity supplied will change as well. And in turn, this will happen if any factor has been affecting u2t, all factors or any other factors except the price, including strikes, weather, import or export, restrictions, any other factor that may affect the quantity supplied from a specific commodity has changed, whether upward or downward, a shift whether upward or downward. So if the quantity supplied again changed for any other reason except the price, so again due to the equilibrium condition, this change or this shift in the quantity supplied will cause a shift in both the quantity demanded and the price. So finally, a change in u1 will cause a change in the price. A change in u1 will cause a change in the quantity demanded and therefore a change in the price. And the change in u2 will cause a change in the quantity supplied and in turn the price, which means that u1 and t and pt in the first equation are not independent, and u2 and pt in the second equation are not independent as well. Actually, this is because of the simultaneous dependence between q and p. u1 and p in one hand and U2 and P in the other cannot be independent. Actually, this can be more explained using the following figures. Now let me give you a common and famous example of simultaneous equation, which is the demand-supply function. Of course, we know that quantity demanded can be represented using the price, and the quantity supplied again can be represented by the price, and it can be represented by this figure here. Of course, you know that this is the demand and this is the supply, and this is the equilibrium point specifying the quantity and the price. So again, let us assume that the demand has been shifted to a new one due to the other factors or due to the error due to U1. So the demand has shifted. And due to this shift in the demand, the equilibrium point changed from this one to a new equilibrium point, specifying new price from P0 to P1. So due to a change or a shift in the quantity demanded, the price has changed from P0 to P1. So U1 and P are not independent, because when U1 shifted, affecting quantity, the quantity in turn will affect the price. So there is a two-way influence. And again for the quantity supplied, if there is a shift in the supply, and again this shift in the supply is due to the other factors except the price represented by U2. So if there is a shift in the price, then again the equilibrium point will change from this point to this point. And this in turn will make the price change from P0 to P1. So a shift in the supply due to a shift in the error term will cause the price to shift as well or to change as well, meaning that the error term and the price are not independent. In the first equation, U1 and PT are not independent, U2 and PT are not independent, which violates the assumption of the OLS, stating that the error term and the explanatory term are not correlated. Now, this is another example for representing simultaneous equation, which is the Keynesian model of income determination. The first equation specifies the consumption function in terms of the income. So C is the consumption and Y is the income. But of course, we all know that the income is specified using the consumption and the saving or investment. I represent investment, which is equivalent to S, which is saving. So YT equal the consumption plus the saving. Your income actually equal what you are consuming plus what you are saving. And the consumption is represented as a function in the income YT. And again, this can be represented by the following figure. So now we want to check whether U and Y, the error term, and Y, the income, are independent or not. Again, let us assume that UT has changed to any other reason. The factors affecting consumption has changed, whether upward or downward. The factors affecting consumption change except income, for example. So when changing these factors, the error term, of course, the consumption will change. And when changing the consumption, YT will change as well. The income will change as well. So increasing your consumption may force you to increase your income in somehow, for example. So we have a relationship between UT and YT. UT and YT are not independent anymore because a change in U causes a change in C, and this change in C will cause in turn a change in Y. So U and Y are not independent, which violates the assumption of the OLS. Now, let us prove that the explanatory variable yt, the income, and the error term ut are not independent. So from equation number 2, which is yt equal ct plus it, we are going to replace ct by beta naught plus beta 1 yt plus ut. So we will have yt equal beta naught plus beta 1 yt plus ut plus it. And then we will have yt minus beta 1 yt equal beta naught plus u plus I. And by taking y as a common factor, we will have y multiplied by 1 minus beta 1 equal beta naught plus u plus I. Dividing by y minus beta 1, we will have y equal beta naught over 1 minus beta 1, u over 1 minus beta 1, and finally I divided by 1 minus beta 1. Now the first term is simply a constant. Beta naught over 1 minus beta 1 is simply a constant. So after taking the expected value for both sides, we will have expected value of y equal beta naught over 1 minus beta 1. This is constant. And then remember that the expected value of u equals 0. So this term will be cancelled. And remember that I is an explanatory variable. It's deterministic. So again, we have expected value equal 1 over 1 minus beta 1 I. So y minus expected value of y, remember that y equal c plus I. And expected value of y equal beta naught over 1 minus beta 1 plus 1 over 1 minus beta 1 I. So subtracting expected value of y from y, we will have y minus expected value of y with an only remaining term equal u over 1 minus beta 1. So now y minus expected value of y equal u over 1 minus beta 1. And of course, as we said, you know that expected value of u equals 0. So u minus expected value of u equal u. So we have y minus expected value of y equals u over 1 minus beta 1. And u minus expected value of u equals u. By obtaining the covariance between y and u, y, in order to prove that they are independent or not, to show whether they are independent or not. So taking the covariance between u and y, we have expected value. By definition, it equals expected value of y minus expected value of y multiplied by u minus expected value of u, which is equal expected value of u squared over 1 minus beta 1, which is equal sigma squared over 1 minus beta 1, and of course this quantity does not equal 0. So the covariance between y and u does not equal 0. So y and u are not independent. Therefore, one of the important assumptions of the OLS method is violated. So finally, we can conclude that the method of least squares, the OLS method, may not be applied to estimate a single equation in a system of simultaneous equations. Why? Because one or more of the explanatory variables are correlated with the disturbance term, which violates an important assumption of the OLS, resulting in estimators that are biased and inconsistent. And actually, this is the problem of simultaneous equation, which is the correlation between the disturbance term and the explanatory variable. And in the next lecture, we will see how to deal with this problem, how to deal with simultaneous equations where we have disturbance term and explanatory variable that are correlated. Thank you so much.